This video is about solving exponential and other equations. We'll talk about solving exponential equations using like bases. We'll talk about solving equations with fractional exponents and also solving equations using exponent rules. Let's get started. We're going to start this really slow, okay? And we're solving exponential equations. Again, exponential equations are equations where the variable is in the exponent. So if you have if you have 2 to the x power equals 2 to the third power, it makes sense that x is equal to 3. Those are the same, okay? Because, and this is the important piece, if you have the same base of the exponent, then the exponents will also be equal to each other. Okay? In letter B, 2 to the x equals 2, well, I can think about 2 as in 2 to the first power, and if the bases are the same, then the exponents have to be the same, and x must be 1. C is where it gets a little more interesting. If 2 to the power of x is equal to 16, then what is x? And that isn't as obvious as A and B. But I do know that 16 is 2 to the power of 4. So if I write it as 2 to the power of 4 and I get the same base of the exponent, then if the bases are the same, then so are the exponents, and x must be 4. Okay? And that's really the key to solving equations with like bases. If you can write them as the same base, then you put the exponents equal to each other and solve. In letter D, let me switch colors here because I've been using red for a while. In letter D, I have 2 to the x minus 64 is 0, and I'd rather deal with the 64 on the other side of the equal sign. So let me do the opposite of subtracting 64. I'm going to add 64 to both sides, and I have 2 to the x equals 64. Okay? And now I'm kind of stuck, but I do know that 64 is a power of 2. It is 2 to the 6th power. So I'm going to write 64 as 2 to the 6th power, and so I have 2 to the x equals 2 to the 6th, and x must be 6. Okay? That's very similar to E. I'll add 1 to both sides. 2 to the x equals 1, and I can write 1 as 2 to a power. It's 2 to the 0th power. And so if the base are the same, then so are the exponents, and x equals 0. Okay, that's really the essence of what we're doing for this first bit, and that is you write them as the same base, and then the exponents must be the same. Okay, we'll put that kind of into steps for you if that's helpful for you. Okay, so I'll solve this. 2 to the x plus 3 is equal to 64. So I'll first rewrite with a common base. In this case, that base is going to be 2. So again, 64 is 2 to the 6th power, so I'll write it with the same base, and I have 2 to the x plus 3 is equal to 2 to the 6th power. The next thing I'll do is set exponents equal to each other. So x plus 3 is going to be equal to 6. Okay? And now we get an equation that we are much more comfortable solving. So now I'm just going to solve for x. In this case, I will subtract 3 from both sides, and I get x equals 3. Okay? So that's really what we're doing. We're writing it with a common base, and then we're solving. Okay? We did one very much like that, example 2. Let's look at example 1. So I have 4 to the power of 3x and 2 to the power of 5x minus 7. I want to write those with the same base, okay? And that's going to be the base of 2. So I'm going to write 4 as 2 squared, okay? That's 4, and that's being raised to the power of 3x. And that's equal to 2 to the power of 5x minus 7, okay? And then I will use the power rule, and I will multiply these exponents together, and I get 2 to the power of 6x. Is equal to 2 to the power of 5x minus 7. And then, because the base is the same, I'm going to write the exponents to be the same. So I know that 6x is equal to 5x minus 7. Okay? And I will solve for x by subtracting 5x from both sides. and I get x equals -7. Okay? So that's really it. I want to show you another kind of problem where it's not so obvious what the base should be. So let's look at like number 3 here. Okay, in number 3, I have 64 to the power of 2x is equal to 16. And the reason it's tricky or different from the previous ones is that 64 is not a power of 16. So you can't get in the habit of thinking, well, it's the smaller number, to some power is the other one. That doesn't work here. So I got to think through, are there any numbers that have powers that are both 16 and 64? And actually 2 and 4 both work. I'm going to use 4. If you use the bigger numbers, then your exponents are a little bit smaller to deal with, but you could do it with 2 as well. I'm going to use 4. 64 is 4 cubed. So I'll write 64 as 4 cubed to the power of 2x. 16 is 4 squared. Okay, and then I'll use the power rule by multiplying 3 and 2x. I get 4 to the power of 6x is equal to 4 squared. And then because the bases are the same, the exponents must be the same. And 6x is equal to 2. And then I'll round this off by dividing both sides by 6. And x is equal to 1/3. Okay, that's solving exponential equations using like bases. Now for some of those other equations. If you can't find a common base, try solving in other ways, such as simplify and raise both sides to the reciprocal power. All right, so if you have an equation where your variable is raised to some fractional power, then the reciprocal of that power is a really nice strategy. Okay, let's actually see one like that before I finish this sentence. So example 3, we notice that we have x to the 2/3 power. Okay, but I only have one x in this equation. So I can think of it like it's linear, even though it really isn't linear. I can think of it like it's linear and solve it as if x was by itself. So I'm going to add 7 to both sides, and I get 2x to the 2/3 is equal to 18. Okay, now it's really a common mistake to think that it's 2x to the power of 2/3, but really it's just x being raised to the power of 2/3. And so I can divide both sides by 2 and get rid of this 2 and just have x by itself. X to the 2/3 is equal to 9. All right, so now we're kind of stuck. I have to deal with that exponent. And that, again, that reciprocal power is really powerful for us. So I can raise both sides to the power of the reciprocal of 2/3. I flip that fraction over and get 3/2. Okay, now on the left-hand side, I will multiply the fractions and they cancel out, which is why I use the reciprocal to begin with, and I have just x. Okay, now you could go to your calculator and plug 9 to the power of 3/2 and you get your answer, but I want to show you how you can think this through without using your calculator. You can first think about the 2 on the denominator, that's where the root is, and the square root, because it's 2, the square root of 9 is 3, and then you think about the numerator, and 3 cubed is 27. So you can think that through and think about fractional exponents in your head if you know your powers and your roots and your square roots and stuff. Okay, so that's using a reciprocal exponent as a way to solve these equations where you have a fractional exponent. Okay, another option for you is you can use exponent rules. So you can do things like rewrite as radicals or fractional exponents, and simplify. You can also use various exponent and inverse properties. Let's look at 2 like this. Let's first look at number 4, and I have 5 is equal to 3 plus the 4th root of 2x plus 1. Okay, my first task will be to get that 4th root by itself, and I'll do that by subtracting 3 from both sides. Okay, and I get 2 is equal to the fourth root of 2x plus 1. Okay, now I'm going to use an inverse and think through what is the inverse, what's the opposite of a fourth root. The opposite of a fourth root is raising it to the fourth power. Okay, 2 to the fourth power is 16. Okay, and the fourth root and the fourth power cancel each other out just like a square root and a square are inverse operations. And so we get 16 is equal to 2x plus 1. And from here, we've done things like this before. So I'm going to subtract 1 from both sides. And then the opposite of times 2 is divide by 2. And x is equal to 15 halves. Or if you prefer decimals, 7.5. Okay, that's just using inverse operations and knowing that a fourth root is opposite of the fourth power. Okay, now number 7 looks really crazy, and you're like, what? I have a fourth root inside of a square root, and that's crazy. So let me rewrite this. Now, one of the tools we have is our exponent rules. So I know that a square root, this square root right here, is the same as raising it to the power of 1/2. Okay? And then in here I have the fourth root, this green one. I have the fourth root, but I have it being raised to the fifth power. And so I'm going to think about that piece with a fractional exponent of power over root to the 5/4 power. So I have k minus 21 is equal to, k minus 21 to the 5/4 power to the 1/2 power. Okay, now you're probably thinking that's still crazy, and I agree, it is a little bit crazy. Okay, but we'll get there, don't worry. Okay, that's equal to k minus 21 to the power of x. All right, so using the power rule, I have an exponent to an exponent, okay? Now I can multiply these together to simplify that, okay? Whereas with the radicals, there isn't really a way to think through how to smush together or combine together a square root and a fourth root, okay? But what you do get with in exponents is 5 times 1 is 5, 4 times 2 is 8. Okay, so you get the 5/8 power of k minus 21 equals k minus 21 to the x power. Okay, now I'm asked to solve for x, not k, and then I realize, holy cow, we have the same base. This k minus 21, even though it looks super scary, it's the same scary something. And so if the base is the same, then so are the exponents. And then we have x is equal to just 5/8, and like we surprisingly were done quick. Okay, so you can use various exponent properties to also solve some equations. All right, this video is about solving exponential and other equations. We talked about solving exponential equations using like bases, and then using various exponent rules to solve some other kinds of equations. Thank you so much for watching.